A little bit about earthquakes and subduction zones. She's going to do more of the same, except in this case, this is going to be more of a technical talk, where she's going to talk a little bit about seismic tomography, the actual technique, and how we use it to image the actual subduction zones, which are places where the plates are descending beneath other plates. And she's at Southern Methodist University. She's an associate professor. She has a bachelor's degree from SMU. She has her PhD from the University of California at Santa Clara in geophysics. And we're very, very happy to have her here. So let's welcome Dr. Heather DeShon.
Okay, so this is a very technical talk. So if you have questions, just ask, okay? If I don't see you, raise your hand, just speak up. All right, so these first few slides, and you have to understand, sometimes I give this talk, this is the only talk I give at a university. So these first few slides are related to the NSF program that helps fund the fact that I can come and talk to you today. So this is the Geo Prisms program. And if you were at an earlier talk, you've seen this slide, but Geo Prisms is a program that investigates the coupled geodynamics, Earth surface processes, and climate interactions that build and modify continental margins. The key reason the National Science Foundation funds the Geo Prisms program and the program before it called Margins is that within the bureaucracy of NSF, there's really no clear place to go to get money to study processes that occur both onshore and on land, so systems that cross the shoreline. So one nice thing about the Geo Prisms program is if you're interested in subduction megathrust earthquakes like I am, these big earthquakes that occur on the plate interface where oceanic lithosphere is subducting beneath overriding continental crust is what I'm most concerned with, then Geo Prisms is where you would go to fund your onshore, offshore seismic experiments. Again, it works as two initiatives. It has both a subduction cycle and deformation initiative and a rifting initiation and evolution initiative. It works through finding questions that are different or maybe related between the two initiatives, and it also works through primary sites. This means if you're interested in subduction megathrust earthquakes, Geo Prisms will be particularly interested in proposals that study Alaska, Cascadia, or New Zealand this time around. The Margins program before that was particularly interested in proposals that studied Costa Rica, Nicaragua, and Japan. So much of the work I'm showing you today is actually funded through the previous program, the Margins program that is now known as Geo Prisms. So the Geo Prisms program and scientists interested in subduction and rift processes came together and put together some key questions for subduction cycles and deformation. This includes the one I focused on this morning, what governs the size, location, and frequency of great earthquakes, and really trying to understand what controls the different types of slip processes we see going on in subduction zones. Another question, how does deformation across the subduction plate boundary evolve in space and time through the seismic cycle and beyond? And there's also space for more subduction factory or trench to arc sorts of questions, including how are volatiles released and transferred through the subduction system? Does that affect what happens to the earthquakes along the subduction megathrust fault? And essentially, ultimately goes to questions of how does arc magmatism work? How does that help us build continental crust? Those sorts of things. So these are more along the lines of subduction as the great water recycler, for example. So here's my movie. This talk today is about, it's going to be a comparative study between the Sumatra subduction zone, or the Sunda subduction zone, and Costa Rica and Nicaragua, where there's been a lot of focused geophysics experiments taking place. But broadly speaking, we're still interested from a tsunami and seismic hazard perspective in understanding, there it goes, so the seismic and tsunami hazard associated with large subduction megathrust earthquakes. So the oceanic plate is subducting during the interseismic period. It pulls down the upper plate along with it. That stored elastic potential is released in an earthquake. And in the case of subduction zones, which lie in marine environments, you may or may not displace enough water column to generate a large tsunami. This is actually particularly relevant image for Sumatra. This comes from Caltech, who's done a lot of work in Sumatra. When we look at Sumatra, there's going to be the island of Sumatra, but there's this string of islands in the forearc that pop up, and it turns out that these are all corals, right? There's coral all along these islands. And so during the interseismic period, these corals get pulled underwater and they thrive, they live, they add new coral, and then after the earthquake, they pop up out of the water and they die off. And so the corals have actually recorded multiple seismic cycles where they've been pulled down into the water during the interseismic and popped up, right? And so you can actually use the coral heads to look at the history of great earthquakes in Sumatra. So that's what this geometry is particularly relevant for. So today I'm just going to go over a comparison between Sumatra and Costa Rica using earthquake relocation and tomography. So as where my morning talk was kind of an overview of things we've learned through earthquakes, whether or not it was my work, this talk this afternoon is really mostly stuff I've been working on. All right, so why two margins? First, they have some big picture differences. Sunda or Sumatra is the site of great megathrust earthquakes. The 2004 magnitude 9.2 Sumatra earthquake and a series of magnitude high 8s. Since then, it's a very long subduction zone, right? The 2004 Sumatra earthquake ruptured 1,300 kilometers, and that was only a portion of the entire subduction zone length. It's an accretionary margin, Sumatra. This means that there's a big, thick pile of sediments coming in on the oceanic plate, mostly from erosion from the Himalayas, actually, so the Bengal fan. So there's a lot of sediment coming in, and as it reaches the trench, it gets accreted to the upper plate. So what you end up with is this large accretionary prism where material gets added to the front end of the system. So this is not unlike Cascadia, for example. Because it's such a big system and because of where it is in the world, and in part because of the US's international relationship with Indonesia, it's really hard to go put seismometers on the ground right above this particular subduction zone, right? First of all, you'd need ocean bottom seismometers. That's incredibly expensive. We're talking about the Andaman Islands, the Nicobar Islands, even Indonesia. These are not places where they welcome US research ships. So instead, what we have is what I call regional or teleseismic data. So these are stations located further away from the earthquakes, technically regional, maybe 10 degrees, teleseismic, anything greater than 20 degrees away. So what that means is that the magnitude of earthquake that you can study goes up, right? An event has to be pretty big, magnitude 3.5 or 4 in order to get recorded on these regional or global seismic networks. All right, this is a very different situation than in Costa Rica. So Costa Rica and Nicaragua, right, along the Middle American Trench, Central America, well, down in Costa Rica and Nicaragua, there is no history of great earthquakes. A magnitude 8, yes. A magnitude 9, not that we know of. All right? It's considered an erosional margin. So there's a very thin layer of sediments that come into the trench. Most of those get subducted. And in fact, It's an erosional system because instead of growing the upper plate, what you're actually doing is eroding the upper plate during the process of subduction from below. Right? So very, very different, accretionary system versus an erosional system. Now we're going to look at only 500 kilometers of Costa Rica, Nicaragua, but this is going to be a small, highly variable 500 kilometers. We're at the southern end of the subduction zone, basically. But because of funding interest by both the National Science Foundation and also international groups, and particularly the Germans, there is a lot of local earthquake data. And what this means is we have peppered southern Nicaragua and Costa Rica with both land seismometers and ocean bottom seismometers, which has allowed us to record tens of thousands of very small magnitude earthquakes along the plate interface. Right, so very different data sets. This is expensive. This you can do from any computer anywhere with a good internet connection. So the big overarching goal here is how can we use this data to answer questions that we thought we could originally only answer with this data. All right? So that's kind of where my overall research program is going. I've done this, and now I'm trying to get this better, more accurate, so that we can study more subduction zones in greater detail. All right, but let's start with Costa Rica and Nicaragua. So Costa Rica and Nicaragua lies at the southern extent of the Middle America Trench, where we have Cocos Plate, derived from the Cocos-Nazca Spreading Center in the East Pacific Rise, subducting under Caribbean Plate, mostly Caribbean plates. The southernest part of Costa Rica is actually involved in this microblock formation with Panama. The interesting thing is that this yellow line marks the boundary between this oceanic lithosphere formed along Cocos-Nazca and this oceanic lithosphere formed along East Pacific Rise. This means there's age differences set up across this boundary, and the Cocos-Nazca lithosphere in particular has passed over what's just off this map, which is the Galapagos hotspot. So the Cocos Ridge here marks the passage of Cocos-Nazca derived crust over, or lithosphere over the hotspot. So it's a very thick, buoyant ridge. All right, so here's a blow up of our study area. Again, here's the East Pacific Rise crust. Here's this Cocos-Nazca crust. You can see already that the East Pacific Rise crust is a lot smoother than the Cocos-Nazca crust. There's actually a change in ridge orientation. So we have two little pieces of Cocos-Nazca related material subducting off of Costa Rica. And it's a little hard to see at the bathymetry at this scale, but another big difference here is that as you move away from the end of the subduction zone, you start to get these large outer rise normal faults that get progressively larger as you move to the north. So when we get into the more detailed maps that show the higher bathymetry, make sure you look for these outer rise normal faults. This is just to show a history of significant earthquakes, including a magnitude 7.3 in 1983, magnitude 7.7 in 1950, and this tsunami earthquake in 1992. So up until some of the more recent tsunami earthquakes, this had been the most well-recorded tsunami earthquakes. So those were the really shallow earthquakes I talked about this weekend, or earlier today, that generate abnormally large tsunami for their surface wave magnitude. This is a good size earthquake. This is a good size earthquake. They're related to the peninsulas. In between, we've never recorded anything larger than a magnitude 7. All right. Now, this purple star occurred in 1950. Before that, there had been a similar size earthquake in 1900. So the thought was that the Nicoya Peninsula, this northern peninsula, had a recurrence interval for kind of the maximum size of earthquake for this area of about 50 years. So that's one of the reasons Costa Rica was chosen for study, because we were expecting to record a big earthquake. That earthquake happened in September of 2012. So this focal mechanism here represents a magnitude 7.6 earthquake that occurred on the Nicoya Peninsula. It actually, it caused some damage. Didn't really cause a lot of lives, but it turns out to be incredibly well documented because especially Andy Newman at Georgia Tech has kept the Nicoya Peninsula very well monitored using geodetic and seismic data since these original studies, which were carried out in the late 90s, early 2000s. All right, so I talked a little bit about changes occurring in the oceanic lithosphere. Let's talk a little bit about this upper plate. There are significant changes in both the volcanic arc and the upper plate. It turns out that there are, you can think of Costa Rica as being this Chortega block of crust, pretty thick continental velocity material. We have the Chortis block up here. This portion of Nicaragua and to the north is some sort of accreted terrain, and I want to draw your attention to this offset that occurs in the volcanic arc, almost coincident with what happened to be the national boundaries. That is related to a big change that occurs in the geochemistry of the magmas coming out of this arc system. So starting down here in Costa Rica, what I'm showing is barium-lanthanum ratios versus distance. So we have Costa Rica up to Guatemala. And the key point is that some of the highest barium-lanthanum ratios in arc lavas in the world are coming out of these Nicaraguan volcanoes. So I'm not a geochemist. My take home, I ask, oh, what does that mean? That essentially means that there is a lot of water in the system, that these volcanoes are seeing a lot of fluids coming up from the slab. So in particular, these are slab-related fluids. So the oceanic fluids carried down by the oceanic lithosphere and then being recycled through the volcanic system. All right. So this is just to reinforce this idea that a lot of people have spent a lot of money to understand Costa Rica and Nicaragua over the last decade or so. All these lines are either right-angle refraction or reflection profiles. There's high resolution bathymetry available for this entire area. A lot of the circles represent seismic lines. Here's a huge wide-angle experiment that took place across the peninsula. But this is all data that I can compare to, because what I'm actually interested in, what I do, is I use seismic data. So all of the circles on this map represent seismometers, either ocean seismometers or land seismometers that have been deployed by either US groups or German groups. So we have a nice set of onshore, offshore seismic data, more seismic data, and you might not be able to tell, but both Nicaragua and Costa Rica run their own short period, mostly short period vertical component country-wide networks. All right. Oh, and shown also on this map are ODP drill sites. So they've done, there is some drilling that's taken place off in Nicoya. And then down here, which would be a whole nother set of two talks, is international drilling focused on drilling directly into the seismogenic zone under a project called CRISP. And that project is just getting started. They've drilled just their first few holes. All right, so what do we already know? Obviously, we've done 10 or some years of research. We should know quite a bit, so what can I add to that? First, right, we know that the oceanic plate varies in age and morphology. We have been able to track changes in the temperature related to that age and or pore fluid pressure along strike, and seen that as you move from Cocos-Nazca crust into East Pacific Rise crust, you move from hotter oceanic lithosphere to cooler oceanic lithosphere, and there is a subsequent very small 5-kilometer depression in the East Pacific Rise side to where you actually start to generate microseismicity. So microseismicity begins slightly further into the system off of Nicaragua and just the northernest part of Costa Rica. We've also seen that these outer rise normal faults that I talk about developing really nicely off of Nicaragua seem to be fluxing a lot of water into the oceanic mantle. And what this does, you add water to peridotite, you serpentinize the mantle, so all that water gets sucked up right into the rock. When that happens, it's accompanied by a reduction in P-wave velocity. So when I say we've seen this with the seismic data. So that's what this shows. So this is a active source seismic experiment that was conducted from northern Costa Rica into Nicaragua along parallel to the subducting trench, all right? So this is a cut through the oceanic lithosphere. The crust is this pale yellow line here. So the crust is about 10 or 11 kilometers thick. So everything below this is mantle. So this is kind of normal. And then as you move further into Nicaragua, you see these really reduced P-wave velocities. So if this is normal up here in the purples, down here you're seeing reds. So if this is water, this is the water that we're seeing come back out the arc lavas in Nicaragua. So when I say a lot of water is getting into the system, they're really wet or with really high barium lanthanum ratios. This seems to be linked. We've also seen just large-scale differences in slab and wedge velocities. So what do I mean by that? Here again, Nicaragua and northern Costa Rica. This was a passive source seismic study interested in looking at, again, if there were velocity and attenuation differences between northern Costa Rica and Nicaragua, which would help explain the arc geochemistry. What's shown here is low VPVS or change in VPVS, so low VPVS and high VPVS. So this is the ratio of the P-wave velocity to the shear wave velocity. Should be some indication of fluids in the system. Maybe also temperature, but we're going to interpret it in terms of fluids. So basically, this is from the Toucan project. We see the large-scale differences in slab and wedge velocities and also the hypocenter distribution. So the Wadati-Benioff zone goes much deeper into Nicaragua, or the slab steepens into Nicaragua than in Costa Rica. You get more earthquakes at greater depth in Nicaragua than in Costa Rica too. Anyway, they actually attribute some of this big change to those changes that are seen in the upper plate. So we've seen that the incoming plate is affecting things, such as the arc geochemistry, but also there's some indication that the upper plate, also the changes in the upper plate also play a role in the sort of segmentation we see along this boundary. Now focusing in on the subduction megathrust fault, so now here we're looking, here's the trench. Now we're just looking in Nicaragua. Now these two images are the same. This is absolute P-wave velocity. We've seen that the characteristics of the oceanic plate are also influencing the rupture extent in the subduction zone. In other words, when we're subducting seamounts and kind of broken up oceanic crust like that, we don't get as big of earthquakes as where we are subducting smoother lithosphere or crust. And we've also seen that there is some evidence that it's not just the oceanic lithosphere that's serpentinized, but also just this toe of the upper plate's mantle is serpentinized. And this is important because frictional stability laboratory measurements suggest that if you serpentinize the mantle, you create a material that, depending on which lab, may or may not be able to be involved in rupture during a big earthquake. So that speaks to down dip limit. Is your down dip limit here, where the upper plate's moho intersects the slab, or is your down dip limit here, where you get out of this regime of serpentinized oceanic mantle? So that speaks to changing the size of the fault that you have available to slip, and so has obvious implications on the seismic hazard. What does the geodetic data tell us? 15 years of nearly continuous campaign and continuous GPS data have come up with this very complex picture of interseismic plate coupling. So I showed an image similar to this for Chile earlier today. Basically, the red indicates areas that are fully coupled, or in other words, the geodetic stations on top of this area are moving inland right at plate rates. So if the plate is coming in at 8.4 centimeters per year, which it is, that GPS station is moving inland at 8.4 centimeters per year. So if a big earthquake was to occur, one idea would be this is where most of the slip would be concentrated. So that really has implications for seismic hazard, because that's direct mapping of what could be expected in the next big earthquake, if that is in fact what this is telling us, right? So interseismic plate coupling is complex, and then on here are little gray dots that represent the microseismicity, so these magnitude 2s and 3s that are occurring between big earthquakes. And then also, Costa Rica is one of these subduction zones where the instrumentation is good enough to record tremor. So the orange ellipse represents seismic tremor, one of these slow slip processes. And then these big yellow blobs represent areas of detected slow slip. So you can think of these as areas that the fault is slipping just like it would in an earthquake, but it's taking weeks and months instead of a few seconds, and so no seismic waves are being generated. So it's really interesting that the high locking falls in between these two areas of slow slip. Now we have an excellent test, because about a month after this study was published in the Journal of Geophysical Research, a big magnitude 7.6 earthquake occurred along this peninsula. The big magnitude 7.6 earthquake. So this is its CMT solution. CMT solutions for larger earthquakes reflect where most of the energy was released in the earthquake, not necessarily where the earthquake started. Okay, so boom, at least a portion of that seems to be consistent. It turns out that if all of this had failed, it would have been a magnitude 7.9 earthquake, and instead it was a magnitude 7.6 earthquake. So the prediction would be that not all of the strain that had accumulated that the GPS data was seeing had actually been released in the earthquake. But the other key point is that what we do know is that the geodesy data, the little earthquakes and the big earthquakes and the thermal modeling, which I didn't talk about, they all tell us different limits. So in our search for a golden proxy to define what controls the up dip limit and what controls the down dip limit of this seismogenic zone, Costa Rica would suggest every piece of data you collect tells you something a little bit different, right? So we continue the search. All right, so double difference tomography. This is really what I do, right? So here's my model space, Costa Rica and Nicaragua. Every earthquake has body waves associated with it, right? P waves and S waves. You can measure the arrival times of the P waves and S waves on your seismograms, and you can use that data to do an inversion for P wave velocity and S wave velocity structure in 3 dimensions, if you have the right data and nice ray path coverage. So that would be considered absolute times. you can improve your modeling near source by including something called differential times. So that's this idea that two earthquakes that are located closely in space have P waves that are recorded at the same station, right? And that the difference in travel time that it took this P wave to get to this station and this P wave to get to this station should be a reflection of near source velocity, because after a while they should have the same ray path, right? So all this velocity should be the same, and any differential time information should be a direct reflection of changes in velocity near the source, and also a more accurate measure of the relative location of those two earthquakes. So you think about improving a velocity model helps you take a cloud of seismicity and make it sharper. Using the differential times helps you make that image even sharper still. And then you can do something called waveform cross correlation to even get more accurate differential times that can make your picture sharper still. Okay, so this is all about taking fuzzy images of earthquake distributions and subduction zones and increasing your location accuracy and creating finer, higher resolution images. All right, so what are we dealing with? This study was conducted by Melissa Moore Driscoll as part of her PhD dissertation at the University of Memphis. The Germans were nice enough to collaborate with us and give us all of their arrival times from their 3 experiments. So their 3 experiments are the Nicaragua experiment, and then all of the experiments here in the central Costa Rica area, so Quepos and Jaco. We consider that one experiment. Then we have all of the data that I used in my PhD thesis. So we have all of the data from the 2 US onshore-offshore experiments, the Nicoya Peninsula experiment, and what's called the Osa Peninsula experiment, but really was, it turns out because of the timing, we recorded aftershocks of this magnitude 6.9 earthquake. So we have a lot of data. We have tens of thousands of events. You don't want to use tens of thousands of events in your inversion for stability reasons we won't talk about. But these are the data that we do use, about a little over 1,000 earthquakes distributed along the margin. And I'm just going to show you cross sections from A in Nicaragua all the way to F down here in central Costa Rica. And along 3 of those cross sections, we have some thermal modeling to compare to. And why do we compare to thermal modeling? It's because there is a huge amount of literature starting in the 1980s that suggests that the seismogenic zone is controlled by temperature. So you hit 100, 150 degrees C, mineral transitions occur that set up materials that can fail seismically. You hit 350 to 450 degrees C, more and different mineral transitions occur that create mineralogies that cannot rupture in big earthquakes. Slippery things like talc, for example. All right, so the next 5 slides kind of look like this. This is just to orient you at the top. I have P wave velocities on the left. These are shown relative to a starting model, so slow velocities are in red, fast velocities are in blue. Here's the continental moho, so crust, rest of the lithosphere. Then we have VPVS images. This is absolute, so 1.6, kind of at the low end. Average for Costa Rica is 1.78, and blue is again high. And then for comparison, we just have these beach balls, so all of the ones that look like strike-slip earthquakes, these have been cut through vertically, so anything that looks like a strike-slip earthquake is thrusting along the slab plate or along the plate interface. And then just for comparison, we have one of these teleseismic catalogs. All right, so all these little black dots are our relocations for the subduction zone. And if we hadn't gone and collected all this data, this is what we would have. All right, so this is what the regional and teleseismic catalog gets you. This is what these local studies get you. The first thing we notice here is that there's just a lot of red. Slow slab P wave velocities. So this is actually pretty consistent with the active source data. So this down here is oceanic mantle. We see low P wave velocities. What we don't see is a really fast slab. So what we should see is a nice big blue slab-like structure that looks like subducting oceanic lithosphere. And we see that as we move just slightly to the south of the Santa Elena Peninsula. So our resolution is also improving as we move to the south. So we start to see our nice fast slab. It's a pretty abrupt transition we actually see between Costa Rica and Nicaragua. So that was one of our questions was, okay, well, we know there's a transition, but is it an abrupt transition or is it smooth and we just didn't collect the data in the area that the transition occurred in? So we see a pretty abrupt transition and we start to see more continuous seismogenic zone, and the earthquakes appear associated with this reduced P-wave velocity that sits on top of our slab. Moving into northern Nicaragua, we now have a temperature model. So we have the 100 degree C and the 400 degree C thermal model or temperature contours shown here. Again, we see all the microseismicity is associated with this nice linear low VP feature, and where the resolution should be really good here in Nicoya. So this is also a low VPVS feature. So I'm going to get to why this matters at the end, because this is the big take-home. We still see that same sort of thing as we move into southern Nicoya Peninsula, but we start to see, now I know you can't see this from the back, but if you were standing right where I am, you'd actually see that this almost looks imbricated. So instead of just a nice linear set of seismicity, it's almost like we see some streaking in the seismicity. It might be a little clearer on the VPVS image. Now we move into central Costa Rica, where we have all these seamounts subducting. Image changes again. We still have a nice, what I would term microseismicity seismogenic zone, but here we have a whole bunch of seismicity occurring in the upper plate. Now, these are not mislocated, okay? I mean, that's the point of using these advanced techniques. It turns out that there's all of this upper crustal faulting going on as Panama tries to rotate. In fact, there's a little bit of subduction on the Caribbean side of Costa Rica as the Caribbean plate's actually subducting back under this Panama microplate. So what I think this is just those faults have to intersect with the subduction zone somewhere. Those upper plate faults associated with this microplate actually create some big strike slip events that tend to have shaking that most affects San Jose, the capital city, than even the subduction zone earthquakes. So that might be what that's related to. But we still have this low P wave anomaly. Now we get into that aftershock sequence. We think this was an aftershock sequence related to subduction of a pretty good-sized seamount or small oceanic plateau. Since this is an aftershock sequence, we're seeing seismicity get activated all across the system. So we see seismicity in the outer rise, we see seismicity in the incoming oceanic crust and lithosphere. We see seismicity associated with the plate interface, as we would expect. So this is kind of a different sort of seismicity distribution that I'd shown you before, and that's because it's an aftershock sequence. All right, but the big feature we see is these are depth slices at 20 to 25 kilometers depth. Basically, this is the plate interface seismicity, and it seems to be associated with this low VP and low VPVS region. Now, this is different than just serpentinizing something. If you serpentinize peridotite, you reduce VP, but you're adding lots of fluids, so you actually reduce S-wave velocity faster. And so one of the seismic clues of serpentinization is reduced VP, but really high VPVS. So what I'm showing you here are images that suggest reduced VP and reduced VPVS. So something altogether different, not fluids. Or maybe related, but not actually like serpentinite. So a summary of observations. This is Nicaragua. This is Costa Rica. Slab is steeper here. We have more highly serpentinized oceanic mantle coming in off of Nicaragua. We have an area where serpentinization in the upper mantle wedge, I didn't dwell on that, appears higher than in Costa Rica. But in both places, we have low VP and low VPVS sitting on top of our plate interface. Now, why? In 2011, Damien Safer and Harold Tobin presented a review paper, but also the review paper, as all good review papers do, included a new model, kind of synthesizing maybe what was going on. And in this case, these are fluid guys. What they suggested was that you have all this water sitting in sediments or whatever coming into the system. Some of it gets accreted, but someplace, whether it gets accreted or not, a lot of it goes down. So even in big accretionary systems, a lot of the sediment gets down into the subduction zone. And as all of that stuff is getting smushed and dewatered, you set up an environment of extreme overpressure. Right? Now, as that fluid drains away, either through faulting in the accretionary prism or up into the forearc, your pore pressure drops. Then you start dewatering or doing mineral transitions in your oceanic crust itself, thereby introducing more fluids into the system and driving your pore pressures back up. So they would expect to see extreme overpressure zones on both ends of what we would term the locked seismogenic zone. So they think that the locked seismogenic zone corresponds with this area of moderate overpressure. Now, interestingly enough, if overpressure affects velocity, which it should, our interpretation is that might explain what we're seeing. That our velocity modeling is actually imaging the fluid overpressure situation on the plate interface. It's speculative and unpublished because we haven't actually written it up yet. All right, but does this happen anywhere else? Does any place else see this relationship with low VP and low VPVS associated with their microseismicity? And it turns out, yes, in Japan. This is a paper that shows previous seismicity in black and aftershocks of the 2011 Tohoku earthquake in yellow. Just want to draw your attention to this area. So the Tohoku earthquake happened pretty shallowly, and it had a lot of slip down dip. And it had a lot of aftershocks down dip. So this is a low P-wave velocity anomaly that dips down onto the plate interface and in fact corresponds well with where all this microseismicity, these smaller earthquakes are occurring. Now, for this aftershock sequence, these could be 4s or 5s, but still smaller seismicity. They have an S image, and then they have a Poisson's ratio image. So Poisson's ratio is related to VPVS. High Poisson's ratio is high VPVS. They are tricky. It is hard to see here, but in the velocity images, red indicates slow, but on the Poisson's ratio images, blue indicates slow. So they're actually seeing low VP and low Poisson's ratio, or low VPVS, just like we're seeing associated with this background seismicity. All right. So, summarize. We see variability in the up-dip limit of the microseismicity, shown here by the blue line. But most importantly, our VP and VPVS models indicate that there's long strike changes in the hydration of the slab and in the forearc mantle wedge. And in particular, we think some of these plate interface velocity anomalies may be related to the amount or the degree of overpressure developed along the plate interface. Now remember, using double difference, we should have actually very good control of velocity near our earthquakes. So our images should have actually highest resolution where we had earthquakes. And then overprinted on that is these regions where we see slow slip. So slow slip or tremor, right? So slow slip and tremor appear in regions where we would see high P-wave velocities. So that's an erosional margin. What about Costa Rica? Or, sorry, what about Sumatra? Here is the Sunda subduction system and the history of big earthquakes starting in 2004 that has developed along this system. Now, the 2004 earthquake was tragic, right? But we're going to take a little bit of pragmatic approach and view it as a tomography opportunity, because the aftershock sequence illuminated a section of the seismogenic zone that had very poor resolution prior to the earthquake. So you have, beforehand we might have had 5,500 earthquakes. After, we had an additional 4,000 earthquakes, but these were earthquakes occurring when the global seismic network was at at the time it was at its peak, right? It's always improving, but we have a lot more data. And this is going to allow us to image the entire subduction zone. So here's a 3D P-wave model. We improved the regional velocity model using Jeremy Pesacek at Wisconsin as part of his PhD thesis, improved the regional velocity model using both basically using data through the 2007 earthquake. So this is kind of what you would see. This is a regional velocity model study. In particular, I just want to draw your attention to the slab. So this is a pretty focused velocity image for a subduction zone. I'm not going to dwell on it, but it was a good improvement. Then we take the double difference technique, just the relocation part, and we extend it to teleseismic distances, and we incorporate the use of depth phases. So a depth phase is a P wave that goes up, hits either the land interface or the water interface, gets reflected down, and then travels out to the station. So it turns out this leg of the ray is a very good control on the depth of the earthquake. So if we can use this information, we can get better depths. All right, so what does this give us? Here's our original teleseismic catalog. Here's after using double difference relocation. And I just want to draw your eye to two features. One is this aftershock sequence related to the 2005 Nias earthquake. It's a little cloudy here, nice sharp edge to the up-dip limit of the seismicity following relocation. Another feature is this. So you can kind of see this line of seismicity here. After relocation, it sharpens considerably, and it turns out that projects out to the investigator fracture zone. So this large fracture zone that's getting subducted under Sumatra and seems to be being reused to generate earthquakes down to almost 200 some kilometers depth. So this is oceanic crustal feature still being used to focus seismicity or generate earthquakes down to almost 200 kilometers depth. So that's pretty cool. These sorts of studies allow us to do things like more direct comparison between what is large slip during the main shock and where the aftershocks occur. So this is the 2004 Sumatra event. These contours represent slip, so there's these two pockets of high slip, and you can really see that the aftershocks, if this is where the highest slip happened, the aftershocks are really just releasing leftover energy. They're not overlapping in space. This is just that Nias example again, showing the seismicity before the earthquake and the aftershock sequence. So you can really see those aftershocks really do just ring that northern part of main shock rupture. And if you remember back to the talk earlier today, this blank region out here is what fails as afterslip. I'll show that image a little bit later. For time's sake, I'm going to skip through the CMT solution analysis. Can now start to look at how faulting develops across the system. So the red are plate interface related thrusting, the green are normal faulting, and the blue are strike slips. So this is the strike slip Sumatran fault in the upper plate back here. And you can start to use this data to define your seismogenic zone and compare to thermal modeling. Now the thermal modeling is not very good here because there's actually no heat flow data available. They're just doing this based on heat conduction equations based on the age of the oceanic plate. But some take-homes, most of these I did not prove because I removed so many slides. But essentially, high-resolution double difference relocations using the teleseismic data are revealing really fine-scaled spatial patterns of seismicity associated with the subduction zone. So again, this just goes back to using newer techniques with the available teleseismic data to start to get the more detailed images that you can get using expensive onshore-offshore experiments. For Sumatra in particular, we confirmed that the subduction megathrust seismicity occurs down dip of the Mojo slab. So I didn't dwell on this, but in Costa Rica and Nicaragua, we weren't seeing any sort of seismicity down dip of where the Mojo intersects the plate interface. And that is not the case here in Sumatra. Here along Sumatra, we see seismicity extend well down dip of where the continental Mojo intersects the slab. This is also true in Chile. So basically, the seismicity is more consistent with the thermal proxies in this region than any sort of mechanical differences set up between moving from having crust on crust versus mantle on crust. The other thing we've seen is that the potential for slip all the way to the trench, and hence the tsunami potential, can't be discounted along all the margin. So in 2010, there was a tsunami earthquake following the 2007 event. Up in Nias, there wasn't a tsunami earthquake, there was just this slow slip event that, because it was so slow, didn't displace large enough water volume to cause a tsunami. But what happens in between these two remains to be seen. So in other words, there's probably still room in the subduction zone for a large magnitude 8+ earthquake, and whether or not it ruptures all the way to the trench like the 2004 Sumatra earthquake or stops and leaves a place for a tsunami earthquake, we can't really say. But the potential is probably still there. So final thoughts. Continued improvements in teleseismic location accuracy will hopefully allow us to do more thorough global studies of seismogenic zone properties. I have a master's student working on the Kuriles now using this technique. So we're going to see how it goes. And our ultimate goal is to go from these post-earthquake studies years afterwards to doing this double difference relocation in real time and making it publicly available, of course. The local data is still necessary for truly detailed seismic images of the subduction system, and also just for a more thorough integration with other geophysical data sets. So I'm not trying to displace these large, detailed OBS experiments. I love going and putting out OBS personally, so I would hate to see the need. You'll always be a need for that data. And the great number of megathrust earthquakes since 2004 each one's been unique. Each one's illuminated a broad range of subduction zone types, and each one has generated a lot of teleseismic data that could be used for these more detailed studies. So thank you. Oh yeah, and participate in Geo Prisms.